Here, we would like to use mathematical induction to show that the nth derivative with respect to x of x squared e to the x, so this notation right over here stands for the derivative of order n with respect to x, okay? So the nth derivative of this expression with respect to x is equal to x squared plus 2nx plus n minus 1n, all of that, times e to the x. And this statement holds for every or for all n in the set of whole numbers, okay? And I define the whole numbers to be the non-negative integers, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so on. Okay, so the first step to show that this is true using mathematical induction is the base case, okay? So the base case allows us to make sure that the first domino of the sequence gets toppled over. For our case, the base case occurs when n is equal to 0, because that is the first whole number in the set, the smallest one. Okay, so n equals to 0. The left-hand side, we have the zeroth derivative with respect to x of x squared e to the x. The 0th derivative is actually just the expression itself, so nothing is changed. So we get x squared e to the x. On the right-hand side, we substitute n for 0. We get x squared plus 2 times 0 x plus 0 minus 1 times 0. All of that times e to the x. This is going to be equal to 0. This is going to be equal to 0. So at the end, we still have x squared e to the x. So left-hand side is equal to right-hand side, therefore the base case is true. All right, now we need the induction hypothesis. Which basically states that this statement above is true for some n, for an arbitrary n, for some random fixed n that is an element of the set of the whole numbers, okay? So we say that this is true, this statement holds for some random, for arbitrary n that is an element of the set of whole numbers, okay? So now what this is going to do is that we're going to use the induction hypothesis in the induction step. So the induction step. So what this is trying to do is that if the statement holds for this arbitrary n, okay, would the statement also hold for n plus 1, right, for the next whole number, all right? So what I need to do is that, well, actually, before I even tackle the induction step, let me just expand this out, okay? So x squared plus 2nx plus n minus 1n e to the x. If I expand everything out, well, let me just do that, okay? So I'll have x squared plus 2nx plus n squared minus n e to the x, and this is equal to distributing e to the x. I get x squared e to the x plus 2nx e to the x plus k squared e to the x minus k e to the x. This just makes it so that when I do the induction step, it is easier for me to compare things if I have everything expanded out. Okay, so now to do the induction step, I need to use the induction hypothesis. Okay, so is it true that the n plus first derivative with respect to x of x squared e to the x, is it true that this expression holds if I just substitute all instances of n with, oh wait, this should be n, okay, all instances of n with n plus 1, okay, because I don't know yet, because my induction hypothesis only tells me that this statement holds that this formula holds for a particular n in the set of whole numbers, okay? I don't know that if I were to take the derivative of this again, right? If I were to take the derivative of this again, right? If you take the derivative of the nth derivative, you get the n plus first derivative, okay? I don't know yet that if I were to take the n plus first derivative, that is the same thing as if I take the nth derivative expression right over here, but instead of having n, I have n plus 1, right? That's what I'm trying to say, okay? Because this formula holds when n is equal to n, okay? But if my derivative was the n plus first derivative, is it true that if I could just substitute n here with n plus 1, right? All instances of n with n plus 1, right? That's a question mark, all right? So now what we need to do is that we need to take the derivative of x squared e to the x first, which is equal to the derivative of the nth derivative with respect to x of x squared e to the x. Okay, so we actually know how to do this because the nth derivative of x squared e to the x is right over here. So actually, it is better if we use this expression over here, because this is a polynomial times exponential. So I just have to do product rule once, right? Okay, so the derivative of the first, which is going to be 2x plus 2n, times the second, e to the x, plus, and then the derivative of the second, which is still e to the x, times the first expression, x squared plus 2nx plus n squared minus n. All right, so then I would have to, expand this whole thing out. So I get 2x e to the x plus 2n e to the x plus x squared e to the x plus 2nx e to the x plus n squared e to the x minus n e to the x. Okay, so this is it. Now I could combine terms and simplify things, but that takes too much work. Okay, so I won't do that here. But what I'm trying to verify is that, okay, so here I have the n plus first derivative of x squared e to the x based on my induction hypothesis using the nth derivative of x squared e to the x. Now what I need to verify is that, okay, if I were to just plug in, right? If I were to just plug in n plus 1 into here, okay? Instead of having n, I replace n with n plus 1. Do I indeed get this same expression? Okay, so then let's see. Now what I need to do is that I have x squared plus 2 n plus 1 x plus, and then n plus 1 minus 1 is n, and then n is replaced with n plus 1. And then this is multiplied by a to the x. Because if these two are equal to each other, then I know that this formula right over here is also true for the n plus first derivative. Okay, so let's see. This is equal to distributing e to the x inside, x squared e to the x, plus I will have 2nx e to the x. I'm actually distributing these as well simultaneously. Okay, so I have, and then plus 2x e to the x plus n squared e to the x plus n e to the x. Okay, all right, so let's see what we have over here. So they are not totally the same, but let's see what we can do here. Okay, so let's see if, well, they don't look the same, but they evaluate to be the same thing, I hope. Okay, so we have x squared e to the x. Maybe if I could cancel these two out. 2nx 2x e to the x, 2nx e to the x, that's the same. Okay, we have 2n e to the x minus n e to the x. Actually, this is actually 1n e to the x, and this is 1n e to the x. That cancels out. N squared e to the x, n squared e to the x, 2x e to the x, 2x e to the x. All right, so these two expressions are actually identical to each other. Okay, so that's good. All right, so this concludes that this formula also holds for the n plus 1th case. Okay, so therefore, by the principle of mathematical induction, we have that indeed this statement holds for every n that is an element of the whole numbers. Okay? Because the base case has it where the first domino of the sequence is toppled over. Okay? The induction step makes sure that between any consecutive dominoes, there is actually no barrier that prevents the second domino from being toppling over. Okay, let's say you are between n and n plus 1. So sure, n gets toppled over, but what if there was a barrier between the nth domino and the n plus 1st domino? Okay, there's a wall or something so that subsequent dominoes, like from n plus 1 onwards, will not get toppled over. Okay, so the induction hypothesis is pretty good because the n here is arbitrary, right? So with the induction hypothesis, you're choosing arbitrary n, and then the induction step verifies that the next n, which is the n plus 1st term, gets toppled over. So the induction hypothesis, along with the induction step, checks essentially every single consecutive domino to see whether or not there is some sort of barrier or wall between them. Okay, so this is a really nice question. Typically, you don't really see induction problems involving derivatives. It's usually divisibility or some sort of summation formula. Okay, so yeah, that's it.